Hello. Today we're going to do the infrared spectroscopy, the Rovibrational spectrum of diatomic molecule, and that diatomic molecule is going to be HCl. All right. We need to generate some HCl. We need to hold it in something, and we need to take its spectroscopy. So how are we going to do that? Well, we're going to hold it in a cell that looks like this. This is the gas cell. It's nice and long, right? There's only so much pressure we can get in here. It's just going to be atmospheric pressure. But to get more molecules that can absorb, what we're going to do is we're going to have a long path length, right? So gas cells tend to be long, right? Because liquid cells, they're a cuvette, you know what they look like, but a gas cell is often longer path length, you can get more absorption, okay? But we have to hold the gas in there, so how do we hold it? We got a couple of valves up here, right? They're closed when they're crosswise and open when they're in line with the glass tube. Right? We also have some windows. The windows are very important. They have to let infrared through. So there's sodium chloride. That's right, there's salt. So normally we would take this cell and we would keep it in the desiccator over here, right? We got to keep it in the desiccator to keep it away from water. Humid air messes with those, just likewise your fingers will mess with them. Make sure you keep the windows dry, all right? So normally it would stay in a desiccator. Right now, we're going to have to fill it up with our HCl. We're going to have to generate some HCl. We're going to generate HCl from sodium chloride and sulfuric acid, concentrated sulfuric acid, right? It's got to be concentrated because when you mix sulfuric acid and sodium chloride, you'll generate HCl. But if there's lots of water around, the HCl just will dissociate and dissolve into the water. So we want to have a minimum amount of water. We have concentrated sulfuric acid, we have sodium chloride. Now we don't want anything that absorbs infrared. We don't want, in particular, water vapor and CO2. They're in the atmosphere all the time, and they absorb lots of infrared light. Oh yeah, greenhouse gas. Remember we did the greenhouse effect, yes. So we want to get rid of the CO2. And in fact, we need to measure a background spectrum where we don't have any absorption at all. So how are we going to do that? Well, we need a gas that doesn't absorb. Gases that are nonpolar or that are monatomic do not absorb infrared light because they have no Rovibrational structure. So what are we going to use? We're going to use argon. So I've got argon, a tank of argon hooked up here. And what we're going to do first of all is we're going to take our cell and we're going to purge it with argon, because the argon will get rid of the CO2 and the H2O, and then we can take a background spectrum with no interferences. So I'm just going to open up these two valves. All right, so you have to open them up both so that the argon flows through there, and then just run some argon through, run it through the other side as well, run it through there again, and make sure close those off. And we know then that our cell is totally, or at least as much as practical for this application, it's devoid of CO2 and water. So now I'm going to go off and run a background spectrum. I'll show you how to do that in a moment. Okay, now I'm back. I'll show you how we did that in just a moment. But now what we want to do is generate some HCl, right? And generally you do this in the fume hood. But I don't have a good angle, so you can see in the fume hood as well. I'll be sticking this in the fume hood presently. We don't want to generate a lot of HCl. How are we going to do that? Need some sodium chloride. Really, just take a little bit of sodium chloride. Just, a little bit of sodium chloride, right? A spoonful, not even a spoonful, just a spatula full, right? Because there's always that 1,000 times volume expansion from a solid to a gas, right? So we don't need a whole lot of that. So we'll stick that over on the side. And then we just need a couple of drops, 3-4 drops of sulfuric acid, no more than that. Drops of sulfur. We don't want too much because you're going to have to neutralize it in the end. And so if you put 5-10 mLs of sulfuric acid, concentrated sulfuric acid in there, then you're going to have to clean it up in the end. Right? So now we roll that over toward the, there you go. We roll it over toward the, you can see it bubbling away, right? Ooh, bubble, bubble, bubble. Bubble, bubble, toil and trouble. Okay, so now we've purged this as well beforehand. Right? We purged it so we didn't have any water or H2O in there. Just like we purged our cell. And now we let that build up a little bit. Get these things out of the way. We purged that volume. We purged this volume to get rid of water and CO2 in the gas phase, right? We purged it with argon because argon doesn't absorb infrared. Now we have that bubbling going on. HCl is forming, right? And we've got a pipette ball, and we're going to use that to waft the gas from here into our cells. So we open up these two, we build up the pressure there, right? And we go waft. Now take it off, open it back up, because if you suck back out all the air, it's not a very good idea. It's like waft again, right? And now we can close off the valves, boom, and we should have HCl in here. I'm gonna stick this in the fume hood, so the rest of the HCl just goes out into the fume hood. All right, so now we've got our cell with a nice long path length with some HCl in there. We'll see if it's enough in a moment. Got our salt windows that we keep our hands off of, right? We're allowed to touch this. There's a glass container in here. That's what those are attached to, right? That's on the side. So we just keep our hands on the side. This is going to slip into the infrared spectrometer. So now let's go down to do some infrared spectroscopy. I'll pause and we'll see you again in a moment. Okay, we're down in the IR lab now, and we're going to do some spectroscopy, right? Now, let me give you a little extended bonus coverage on infrared. Right, the infrared spectrometer, there's the infrared spectrometer back there. All right, you can see our cell over to the side. Now, there are several attachments for the infrared spectrometer. There is the ATR, the attenuated internal reflection, attenuated total reflection, ATR, MIR, multiple internal reflection cell. All right, there's a diamond prism down here. The infrared light comes in the side, bounces by total internal reflection through that prism. The prism is exposed to a little hole up at the top. I don't know if you can see the hole just there. That would go underneath this little anvil. And you can do either liquid or solid samples with this one, right? You can take the IR spectrum of those, right? There's an evanescent wave that comes out of the prism, and that probes the material above it. They'll use that in forensics. And then I think they might use it in the inorganic lab too. Then there's a diffuse reflectance attachment. The diffuse reflectance attachment allows you to use a powder or a liquid, or you can put a solid on here like a silicon wafer, right? And you slide that in here, infrared light comes in, it's directed down toward the sample, diffuse reflectance of infrared comes out. There's a gold mirror in here. You collect as much light as you can, send it into your spectrometer, measure an infrared absorption. All right, if one of those two is in here, you need to change it over to the transmission cell. The transmission cell, right? Here we go. They just lift out, right? Okay, so let me put this to the side here, right? The cells just lift out. Boom. Lift out of there. Be careful to lift those out gently like that. There's an alignment hole at the front, an alignment hole at the back. There are two posts that will meet there and there. Those, here, let me show you those. Two posts here and a post there. There are these three electrodes back here. Okay, what do all of those do? The two posts are for lining up the two alignment holes here. Boom. Boom. Okay. There we go. And those three in the back, that tells it which accessory is in there, except that these two don't actually have anything that mates up with that. Only the transmission one. Okay. Notice that on these, there are also these little styrofoam puppies. After you put them in, first you can move them back, and then after you put those attachments in, you would move them all the way out so that they meet the body of the spectrometer. Then the cell, right, is just going to slip right into here. Boom. There's a front slot and a back slot. Doesn't matter which one you use, just be consistent. All right. Then you close this up. and you're almost good to go. Now, depending on how sensitive you are to the background, you may want to purge the entire spectrometer. And you can do that with this nitrogen that we have here. Dry nitrogen can be used to purge, because again, you got to remove CO2 and water vapor, right? Now, inside the spectrometer, this is FTIR, Fourier transform IR. What does it do? There is a glow bar. That's the source. It really is just a hot piece of metal, and it's glowing out the infrared spectrum. That should be a nice, smooth spectrum of light. And then it's got to bounce off a bunch of optics, lenses, some mirrors, right? Focusing optics, whatnot, to get it on the right path through here. And there's also a beam splitter. The beam splitter in this case, what we're using is KBr, potassium bromide beam splitter. Splits the beam into two. Why is that important? Because one path is to go through our sample, and another path is recombined with that, and it forms an interferometer, right? You have two paths, radiation coming out, and you recombine them, and you get them to interfere with each other, and this way you get a spectrum of all frequencies of the infrared light at the same time. Okay, now how are we going to interpret this? How do we get our pattern? Actually, what's important is in that interferometer, there's a mirror on a sled, and it's movable. And if it moves farther, you get more resolution, right? You get more elements in your Fourier transform, and you get more resolution. But if you got to move it farther, it takes longer, right? For higher resolution, it's going to take longer. Now, we don't have to scan in frequency because we get all the frequencies at once in the FTIR. But very often, the signal to noise, right, isn't good enough if we just take one spectrum, and we're going to average them over and over. In the old days, because of the way they did Fourier transform, you always had to take a factor of 2 spectra, 2, 4, 8, 16, 32, 64, 128, right? You don't have to do that anymore, but still very often you'll see that people use a multiple of 2 in the number of spectra that they take in an FTIR, just out of habit, right? Convention. All right, so we don't need to, I did for the high resolution, but in this one, we don't need to purge the whole instrument, right? But for some good data, I just right? But we always need to take a reference, right? The very best data is going to be with a reference, right? Where everything is purged, and you have the cell in here. The cell itself is purged first, right? Okay, because if you have the cell empty and everything else empty, and well, not empty, empty of things that will absorb IR. So you can put a purge gas in there, argon or nitrogen, right? And so if we fill that first with argon, then we get rid of any absorption from the windows, we get any absorption or transmission problems in the spectrometer, we can average out all of those, get rid of them, and then we're going to put our cell in. Now for these preliminary, the preliminary spectra where you're changing parameters, every time you change parameters, you have to take a new background spectrum. You change the number of scans, you have to take a new background spectrum. You change the resolution, you have to take a new background spectrum. And because that would be difficult with going back and forth between having a sample and having a purge cell, having a sample, having a purge cell, for those rough spectra at the beginning, we're just going to use an empty spectrometer, no cell in there as the background. For the really good high resolution spectrum, we need the best possible background. So I purged the whole system, right? I put a cell filled of argon into our chamber, to the sample chamber there. I then waited 5 minutes after opening that because it allows the air in there, and I kept purging it to get rid of water and CO2. And then I took the backup. And for the high resolution one, I did the same thing. I opened it up with the sample in, and I put it in there, and then took the spectrum of the high resolution one after waiting 5 minutes again in order for the whole thing to be purged out again. How long is long enough? Depends on how high, how good of a background you need, right? So it depends. If you're looking in the region for CO2, or if you were working on CO2 and you only want the CO2 to be in your cell and not in the atmosphere, You may have to put the whole thing under vacuum, right? You may have to use the driest of nitrogen, which is what comes from the vent on top of the liquid nitrogen tanks. And if you hear a sudden psh, like you might have heard earlier, that is actually one of the pressure release valves on the liquid nitrogen tank. There's that nitrogen that's coming up out of that vent off the liquid nitrogen. That's the best, driest nitrogen you'll ever get, right? Okay, so that's how we set up the spectrometer side, right? For a background, let's just show you what a background looks like. Right now, we're going to take a background with we're going to take a background of just nothing in there, no cell at all. Okay, so the program that we use is called Omnic. I'm going to start that up. I'm going to start up Omnic, which is the control software for this. And then very often when it opens up, it'll ask you, what do you want to do? And I want to do a transmission experiment, just regular transmission. And sometimes we'll say, what's going on here? I got to move things around. You can hear it. It's going between different beam splitters. It's looking for different optics and things like this. It runs some scans in the background just to make sure everything's working. And then we want to make sure that we have the right thing up here. We don't. And in the collect screen, that's where we can change the number of scans. I'm just going to make it 4 right now. And the resolution, you can pick a number anywhere from 0.125 to 32. All right. A bigger number is actually worse resolution. Right. So let's just set it to 0.5 for right now. 4 spectra. We're going to take transmission %T rather than absorbance. All right, so I set that there. And then over here, you can tell it whether it has to collect a background now, right, before the scan, or if it's from a particular file. For that high resolution one, we're going to use that one particular file, right? So we set that. Then in the second tab over bench, all right, check it out. We've got that KBR beam splitter, yeah, the IR source. And then this is where you can set the frequency on the bench one. And I'm going to go from, just to show you some extra stuff, I'm going to do an expanded range here to go from 4,000 to 600 inverse centimeters. You always have to have a background. Either you have a recorded background or you record a new one. Right now, we've got a background that we're going to use just the air as our background. So even though I say collect sample, it still says, put in a name. Let's just say test 1 for that, whatever the name it is that you want to use. It's going to be your sample. Say OK. And then it's going to say, hey, you need a background because you've got to collect the background for each one. So I'll collect the background. All right. That will be fun. We'll collect the background. And now it always, even though it takes that first spectrum, it doesn't show you anything yet on the screen because it takes at least 4 spectra. It has to add them together before it displays anything. So don't be surprised when it doesn't display anything at first. And then they start to show up. Boom. And now we're going to collect the sample. All right. So take our cell, I slot it in there. Say OK, right? And boom, it will start taking. Now, oh, wait a second. What is going on here? You see all kinds of red. It's bleeding all over the screen. That's the background. Now, we would have expected that the infrared light is actually just a broad featureless from the glow bar. Right? It's just a broad featureless spectrum of light. You can see there's all kinds of structure in there. And that was with nothing in there. All that was in there, right, was the cell. It's nothing in there. And we still had stuff all over the place. Okay, so now I've got things going up, I've got things going down. This is kind of crazy. What's going on? Well, it's ratioing between those two, the background and the reference, right? And there are different regions of the spectrum. This is out around 3,500 to 4,000. That is some overtone lines or some hydrocarbons, overtones of CO2. There's some stuff around 3,000, 2,900. That's actually where the HCl is. That's this region here is where the HCl is going to be. All right. Then there's this stuff in here, and this is actually CO2, really quite small because we got rid of most of that by the purging. There are little bars down below the spectrum. Down here, you can grab these bars if you need to open things up again. You can pick out which part of the spectrum you want to look at. Have some big lines here. That's water. That's water. Stuff in here, that's mainly, there's some glass peaks and whatnot, or big broad structures, and then there's some more water peaks way down at the end. If you need to change the scale, you can go full scale again under view. All right, that's where that is. Okay, what about our HCl? Did we have enough? Did we have enough? You can see some nice big peaks, and they're changing from about 60, 65% transmission is where the background line is, and 35% is the top of the peaks. Hey, we got 30% change. Good, we got plenty of signal. All right, great. Now, that means we're good to go. There are going to be some real changes in the spectrum that occur when we measure under different circumstances, right? If you change the number of samples, number of spectra that you run, right? Change the number, it's going to take longer. It actually tells you up here, estimated time for this collection. It's always an underestimate because there's a little bit of setup time. It said it should have taken 16 seconds to do 4 scans. And if you put 64 scans in there, right, it's going to tell you it's going to take 4 minutes and 20 seconds. It takes a lot longer if you average more scans together because it keeps moving. If you change the resolution from 0.5 to 32, it says, oh, it's only going to take 24 seconds, right? It takes longer to physically move that mirror, and you have to move the mirror further to get higher resolution, right? So higher resolution makes the scans go longer. Taking more scans makes the scans go longer, but higher resolution allows you to resolve, right, these peaks. Oh, look at this, we've got some peaks here. We'll talk about that in a separate video. Got some peaks here. You might be able to see those. All right, you'll see them better later when I get this stuff on Igor, right? Looks like a bunch of doublets. But if you change the resolution, right, you're not going to be able to resolve close-lying peaks to each other, right? If you take more scans, right now there's not a lot of signal to noise back here, and actually our detector is pretty good. There's not a lot of noise in it, but you can get to see some really small peaks if you take more scans. So we're going to go up to, I'm actually going to go to 128 on the one I'm going to give you, and then we'll be able to see a lot more. So we're going to take some data. That data, we're going to change the resolution. We're going to see the effect on that. You're going to get that data and you're going to see what those, you're going to look at those. We're going to change the number of scans. And so we will take a look at those and see how the signal noise improves as you increase the number of scans. We'll see what the resolving power does. It's really pretty amazing on this spectrum. In the range that you're going to look at, there pretty much are just you can see that the HCl part of the spectrum will do a better background. If this is, since we had the cell out, we didn't get a nice flat background. But for the high resolution scans we're going to do, we're going to make sure that we get a nice flat background and be able to tell this. Now, when you're taking your data, there are going to be a whole bunch of peaks there. You're going to have to pick out the peaks. We'll talk more about peak picking and which peaks you want and how to tell what the peaks are. We'll go over that later. Here, there actually is in this program itself, there is an analyze, find peaks, and it allows you to find peaks, right? That's very helpful. And then you can save it. Actually, you can save it to the clipboard and paste it into a Word document or paste it into Excel if you want. All right. Couple of things to be careful about when you save your data. One, The background file has to be in SPA format. That's a format that only this program can read, right? The rest of the data you want to save as a CSV file so you can read it in Igor Pro, right? To find and present, to find the peaks and present the data, right? So make sure about that. Now, when I showed you that, you could zoom in on a region by selecting it and click expand, right? We can zoom in even more and you'll see those, all right? If you zoom in and you save, it will only save this portion of the spectrum. It only saves what is in red, okay? If you have multiple spectra here, right? You have multiple spectra and you save as, it doesn't save all of them, it only saves the one that's in red and it only saves this region. Even though there's all this other data that you took, be careful, right? There may be all of this other data, but if you select just that portion, it's only going to save that portion. Be careful about that. Save it as a CSV file. For the data files that you need, save the background as an SPA because it needs that for being able to use it as a background. Okay? You can get the peaks by find peaks and analyze, right? And then go to clipboard and paste them into. Be careful. If you open it in Excel, Excel might not look at all of the digits that are there. And I've seen some really weird spectra result from that. And they look like they have all these steps in them because you have to tell it to accept at least 3 decimal places, all right? Excel, a lot of times it'll only give you 1 decimal place, then all these, it just looks terrible. Excel is so brain dead, but I've mentioned that before. Okay, so there, I think we've got the data acquisition part, we've got the generation part. We'll talk about the data analysis part later.